Welcome to Ask and Learn.
This question is a little bit of a twist on the traditional calculation of binding energy in joules per nucleon, given the mass of the nuclide. In this case, you're given the joules per nucleon and asked to calculate the mass of the nuclide. The series of calculations are very similar. We're just essentially doing it in reverse. If we know that the energy is 1.326 times 10 to the negative 12 joules per nucleon, we can convert this into joules per nuclide and then joules per mole of nuclides by multiplying by 27 and then Avogadro's number, and we get 2.155996 times 10 to the 13 joules per mole of magnesium 27 nuclides. Knowing this, we can then use E equals the mass defect multiplied by c squared with rearrangement to solve for the mass defect, the difference in mass between the summed mass and the actual mass of the magnesium 27 nuclide. So we'll put in our energy value we just calculated up here in joules per mole and divide by the speed of light squared. And this will give us the mass defect in kilograms per mole. We can convert this to grams per mole by dividing by 1,000. So this is our mass defect, our delta M, which is the difference between the summed mass of the protons, neutrons, and electrons minus the actual mass. So if we put in for delta M the mass value we calculated, and then we determine the summed mass by taking 12 times the mass of a proton plus 15 times the mass of a neutron plus 12 times the mass of an electron, all these in units of grams per proton or per neutron or per electron. This will then give us the summed mass of a single magnesium 27 nuclide in grams. But to compare it to grams per mole, we need to multiply by Avogadro's number in order to get the mass per mole, and then subtract off m, the actual mass. All that's left is a little bit of algebra. Let's determine the value of this sum, 27.223233 grams per mole. Rearrange the equation to solve for m, and we get 26.98334 grams per mole. You may get a value slightly different from this if you choose not to include the electrons, which some people do and some people don't.